Welcome to this video on radioactive decay. We will cover the three types of radiation, their unique properties, their penetrating power, and their real-world applications to help you master these key concepts for your GCSE Physics exams. In this video, we will explore why certain atoms become unstable, look at the three primary types of radiation, examine their penetrating power and ability to cause ionization, and finish with practical uses and essential exam tips. At the heart of every atom is a nucleus, which is composed of protons and neutrons. The number of protons determines the element, and the total count of both defines the mass number. While most nuclei are stable, some are not. When a nucleus has an imbalance of protons and neutrons, or is simply overcrowded, it becomes unstable. To reach a more stable state, the nucleus releases excess energy. This process is called radioactive decay, and atoms that do this are known as radioactive. One of the most important facts about radioactive decay is its randomness. It is impossible to predict when a specific nucleus will decay, and you cannot influence it with heat or pressure. Scientists can only calculate the probability of decay over time. Now let us move to the three types of radiation: alpha, beta, and gamma. Each has distinct structures and behaviors, and knowing how they differ is essential for success on your GCSE exams. First, alpha radiation. An alpha particle consists of 2 protons and 2 neutrons, making it identical to a helium-4 nucleus. It is relatively large and carries a positive charge of +2. Emitting an alpha particle reduces the atomic number by 2 and the mass number by 4. Next is beta radiation. A beta particle is a fast-moving electron ejected from the nucleus when a neutron transforms into a proton. Beta particles have negligible mass and carry a negative charge of -1. This emission increases the atomic number by 1, while the mass number remains unchanged. Finally, we have gamma radiation. These are high-energy electromagnetic waves emitted from an excited nucleus. Gamma emission does not change the atomic number or mass number. These rays have no mass or charge and travel at the speed of light. This table provides a quick comparison of the three radiation types. You can see the differences in their composition, electrical charge, and mass, which are key details to remember. Next, let's discuss ionizing power. As radiation travels through matter, it can knock electrons off atoms, creating ions. The ability to do this varies significantly between alpha, beta, and gamma radiation. Ionization happens when a particle or wave carries enough energy to remove an electron from an atom. In living tissue, this can damage DNA and cells, potentially causing serious health issues. The more strongly ionizing a source is, the more damage it can cause, though it also loses energy more quickly. Alpha particles are the most strongly ionizing. Because they are large, slow, and carry a double positive charge, they interact intensely with nearby atoms, stripping electrons and creating dense ion trails. This interaction causes them to lose energy quickly, meaning they have a very short range. Beta particles are moderately ionizing. They are much smaller and faster than alpha particles and carry a single negative charge. Because they interact less intensely with matter, they can cause ionization over a greater distance and penetrate further into materials than alpha particles. Lastly, gamma rays are the least ionizing because they have no charge or mass. They interact rarely with matter, which allows them to pass through most materials. This high penetrating power makes them the most deeply penetrating form of radiation. This summary table compares the ionizing power of the three types. Alpha is the most strongly ionizing due to its charge and size, beta is moderately ionizing, and gamma is the least ionizing, as it interacts rarely with matter. Now let's explore penetrating power and range. Each type of radiation is blocked by different materials, which is a vital concept for both your exams and understanding safety procedures in environments involving radiation. Range in air varies greatly. Alpha particles have a very short range, traveling only a few centimeters. Beta particles can reach about a meter, while gamma rays have a long range and are effectively unlimited in air. Despite being the most ionizing, alpha particles are the least penetrating. A simple sheet of paper, or even the outer layer of your skin can stop them. They are only dangerous if inhaled or ingested. Beta particles are more penetrating than alpha. They pass right through paper, but are stopped by a few millimeters of aluminum. Because they can penetrate skin, they require careful shielding to avoid burns or internal damage. Gamma rays are the most penetrating and cannot be fully stopped. They can only be reduced in intensity. Thick lead or several meters of concrete are required to attenuate them to safe levels in industrial and medical facilities. This diagram summarizes what stops each type. Notice how the required density of shielding increases as the penetrating power increases. Remember, the best shield depends on the specific type of radiation being blocked. Next, let's look at how radioactive decay actually changes the nucleus. When a decay event occurs, the atomic number and mass number shift according to the specific type of particle or energy emitted. In alpha decay, the nucleus ejects 2 protons and 2 neutrons. This causes the atomic number to decrease by 2 and the mass number by 4, effectively transforming the nucleus into a different element. Beta decay involves a neutron turning into a proton and an electron. The electron is emitted. This increases the atomic number by 1, but the mass number stays the same. Again, a new element is formed. Gamma emission is unique because it causes no change to the nucleus itself. The nucleus simply releases excess energy as a wave, so the atomic number, mass number, and the element identity all remain unchanged. Now that we understand how decay works, let's explore how we use radiation in the real world. It has many critical applications in medicine, industry, and research that extend well beyond the laboratory. Medically, radiation is life-saving. Gamma rays are used in radiotherapy to target and destroy cancer cells. Tracers allow doctors to diagnose internal conditions, and gamma radiation is used to sterilize surgical tools. In industry, radiation is equally important. It is used for thickness gauging during production, as a power source in smoke detectors, and for carbon dating in archaeology to determine the age of organic artifacts. Finally, remember that safety is paramount. When working with radiation, we use lead shielding, tongs, and limit exposure time to keep everyone safe. Proper precautions depend on the type of radiation, the dose, and how the source is handled. Welcome to our final chapter, exam preparation. We are going to focus on consolidating everything we have learned through targeted revision tips, addressing common misconceptions, and using a summary table to lock in those key facts. The golden exam rule: always use precise definitions. Learn that alpha is a helium nucleus, beta is a fast-moving electron, and gamma is an electromagnetic wave. Examiners look for this specific language, so avoid imprecise terms like ray of light for gamma or just electron for beta. Let's clear up common misconceptions. First, alpha is most ionizing, not gamma. Second, decay is entirely random and cannot be controlled by external conditions. And third, gamma emission does not change the nucleus. It only releases excess energy. Remember the inverse rule: as ionizing power increases, penetrating power decreases. Alpha particles cause the most ionization because they deposit energy quickly, which is why they are stopped so easily. Conversely, gamma rays interact rarely, making them highly penetrating. When tackling nuclear equations, follow these 2 rules. The total mass number must be balanced on both sides, and the total atomic number must also be balanced. Checking these sums is the easiest way to verify your answers in an exam. This table is your best friend for revision. It breaks down the composition, charge, ionizing power, penetrating power, and shielding for all 3 radiation types. I recommend writing this table out from memory several times before your exam. Here is a quick summary of how the nucleus changes during decay. Note that alpha decay reduces both numbers, beta decay increases the atomic number by 1, and gamma decay leaves both values unchanged. Memorizing this is vital for completing nuclear equations. Here are 5 essential points to memorize. Alpha is a helium nucleus. Beta is an electron. Gamma is an EM wave. Decay is completely random, and there is an inverse relationship between ionizing and penetrating power. Let's test your knowledge. Given a starting atomic number of 88 and mass number of 226, if it undergoes alpha decay, we subtract 2 from the atomic number and 4 from the mass number. This leaves us with an atomic number of 86 and a mass number of 222. You are ready for the exam. To succeed, make sure to revise these concepts daily, practice writing out those nuclear equations, and work through past paper questions. Thank you for watching, and good luck with your studies.